overview of the OSI model and its 7 layers, you will learn about the function of each layer in a little more detail, starting with the lower layers. In addition to the concepts, you will read about some of the devices that operate at those layers and some of their installation concepts. Physical layer concepts. Generally speaking, physical layer concepts deal with a network component that is tangible or measurable. For example, when a protocol at the physical layer receives information from the upper layers, it translates all the data into signals that can be transmitted on a transmission medium. This process is known as signal encoding. With cable media, the protocols that operate at the physical layer translate the ones and zeros of the data into electrical ons and offs. Additionally, the physical layer specifies how much of the media will be used during data transmission. If a network signal uses all available frequencies, the technology is said to use baseband signaling. Most LAN technologies such as Ethernet use baseband signaling. On the other hand, if a signal uses only one frequency, the technology is said to use broadband signaling. This means multiple signals can be transmitted on the media simultaneously. Television signals use broadband signaling. Finally, the physical layer specifies the layout of the transmission media. A physical topology describes the way the cabling in physical laid out as opposite as opposed to a logical tech as a sorry as opposed to a logical topology. Discussed later in the section, the data link layer. The physical topologies include the following: bus star ring mesh. The bus topology. In a physical bus topology, every computer is directly connected to a common medium. A physical bus network uses one network cable that runs from one end of the network to the other. Workstations connect at various points along this cable. The main advantage of this topology is simplicity. Only one cable is used, and a physical bus topology typically requires less cable than other physical topologies. However, a cable fault can bring down the entire network, thus making the physical bus topology the least fault tolerant of all physical topologies. Star topology. In a physical star topology, the cable runs from each network entity to a central device. This central device, called a hub, allows all devices to communicate as if they were directly connected. The main advantage to the physical star topology is its fault tolerance. If one node or cable malfunctions, the rest of the network is not affected. The hub simply won't be able to communicate with the station attached to that port. An Ethernet 10-base-T network is one example of a network type that requires a physical star topology. Now just bear with me. The ring topology. A physical ring topology isn't seen much in the computer networking world. If you do see it, it's usually in a wide area network WAN environment. In a physical ring topology, every network entity connects directly to only two other network entities, the one immediate preceding it and the one immediately following it. The complexity of the ring topology makes it a poor choice in most network environments. The mesh topology. A physical mesh topology is another physical topology that isn't widely used in computer networks except in special WAN cases. In a physical mesh topology, every computer is directly connected to every other computer in the network. The more computers that are on a mesh network, the more cables that make up the network. If a mesh network has n computers, there will be n 1, 2. With 10 computers, that will be 10, 10 minus 1, 2, or 45 cables. As you can see, this topology quickly becomes unmanageable with only a few computers. Physical layer devices. Several devices operate primarily at the physical layer of the OSI model. These devices manipulate mainly the physical aspects of the network stream, such as voltages, signal direction, and signal strength. Let's take a look at some of the most popular. NIC network interface card, transceivers, repeaters, hub, and multi-MAUs. The network interface card, probably the most common component of any network, is the network interface card, NIC. A network interface card is the component that provides the connection between the computer's internal bus and the network media. Network interface cards come in many shapes and sizes. They vary by the type of bus connection they employ and their network media connection ports. The transceiver. Strictest definition: a transceiver is any part of the network interface that transmits and receives network signals. Transmitter receiver. Every network interface has a transceiver. The appearance and function of the transceiver vary with the type of network cable and topology in use. So I just want to show you, this is a quick picture here of a network interface card, and this would be inserted onto the computer's motherboard. The repeater. The simplest of all physical layer devices is the repeater, which simply amplifies the signals it receives on one port and resends or repeats them on another. Repeaters are used to extend the maximum length of a network segment. They are often used if a network Sorry, they are often used if a few network stations are located far from the rest of the network. The main downfall of a repeater is that it repeats everything it receives on one port, including noise, to its other ports. This has the ultimate effect of limiting the number of repeaters that can practically be used on a network. The 5-4-3 rule indicates how many repeaters can be used on a network and where they can be placed. According to this rule, a single network can have 5 network segments connected by 4 repeaters, with 3 of the segments populated. If this rule is violated, one station may not be able to see the rest of the network. And here is a picture here of a repeater. The hub. After the network interface card, a hub is probably the most common physical layer device found on networks today. A hub, also called a concentrator, serves as a central connection point for several network devices. As its basic level, a hub is nothing more than a multi-port repeater. A hub repeats what it receives on one port to all other ports. It is therefore also subject to the 5-4-3 rule. There are many classifications of hubs, but two of the most important are active and passive. An active hub is usually powered, and it actually amplifies and cleans up the signal it receives, thus doubling the effective segment distance limitation for the specific topology. For example, extending an Ethernet segment around 100 meters. A passive hub is typically unpowered and makes only physical electrical connections. Typically, the maximum segment distance of a particular topology is shortened because the hub takes some power away from the signal strength in order to do its job. So this is a picture of a hub, and as it says, um, if it receives a signal in port 1, then all this signal then will be repeated out on ports 2, 3, 4, and 5. The Multistation Access Unit MAU. This physical layer device is unique to token ring networks. Token ring networks use a physical star topology, yet they use a logical ring topology discussed later. The central device on an Ethernet star topology network is a hub, but on a token ring network, the central device is a multi-station access unit, MAU, sometimes called MSAU. The functionality of the MAU is similar to that of a hub, but the MAU provides the data path that creates the logical ring in a token ring network. The data can travel in an endless loop between stations. MAUs are chained together by connecting the ring out port of one MAU to the ring in port of another, connecting the last out the last ring out port to the ring in of the first MAU in the chain, thus forming a complete loop. In a token ring network, you can have up to 33 MAUs chained together. And this is a picture of a multi-station access unit. The data link layer. The data link layer is actually made up of two sublayers: the media access control (MAC) and the logical link control (LLC). Data link layer concepts. Protocols that operate at the data link layer have several responsibilities, including creating, transmitting, and receiving packets. Additionally, the data link layer is responsible for physical MAC addressing and logical link control (LLC) processing, creating logical topologies, and controlling media access packets. At the data link layer, data coming from upper layer protocols are divided into logical chunks called packets. A packet is a unit of data transmission. Size and format of these packets depend on the transmission technology. The hardware MAC address. Every network interface card has an address, typically assigned at the factory. This address is protocol independent and it's often called a hardware address. It's technically accurate, however, to call it the MAC address because it exists at the MAC sublayer of the data link layer. This address is also called the Ethernet address or physical address. The MAC address itself is a 12-digit hexadecimal number. As you may remember, a hexadecimal uses all digits from 0 through 9 and 8 through F. Each two-digit is separated by colons like 08, 58, AD, 1F, B2, 86. Normally, the MAC address of a network interface card is set at the factory and cannot be changed. For this purpose, all network interface card manufacturers keep track of MAC addresses they use so they don't duplicate addresses between vendors. As of late, however, some manufacturers have started reusing their blocks of MAC addresses. This makes it necessary for administrators to be able to change the MAC address of the cards they receive using a factory supplied programs. So if they discover a duplicate MAC address, they can resolve the conflict. logical topology. In addition to these responsibilities, the data link layer can also dictate the logical topology of a network or the way the packets move through a network. A logical topology differs from a physical topology in that the physical topology dictates the way the cables are laid out. The logical topology dictates the way the information flows. The types of logical topologies are the same as the physical topologies, except the information flow specifies the type of topology to use. Finally, the data link layer can describe the method of media access. The three main methods of access are contention, in which every station competes with other stations for the opportunity to transmit, and each has an equal chance of at transmitting. If two stations transmit at the same time, an error referred to as a collision occurs and the station tries again. Polling, which a central device called a controller polls each device in turn and asks if it has data to transmit. This type of media access virtually eliminates collisions. Token passing, which uses a special data packet called a token. When a station has a token, it can transmit. If it doesn't have the token, it can't transmit. This media access technology also eliminates collision problems. So I'm going to leave it here today for this video. If you liked listening, please consider like, sharing and subscribing, and thanks for listening.